Hello everybody. A microcontroller is a tiny computer. Typically it has a CPU, a RAM, flash, and a bunch of pins that stick out, as you can see in this diagram. The RAM, which translates random access memory, is a volatile memory that is used for temporary storage. We say it is volatile because immediately you cut power to the microcontroller, you lose the data that the RAM stores. When the program is running, the RAM stores things like the variables and the stacks. ROM, on the other hand, read-only memory, is a non-volatile memory that can be used to store firmware or data that doesn't change frequently. Traditionally, ROM is rarely used in modern microcontroller units, but the concept includes storage mechanisms that retain data even when power is cut off. So when power is cut off, the ROM retains its data. The flash memory is a specific type of non-volatile memory, which means that when the power is cut off, all the data that is saved in the flash is retained. Now, the flash is often used in MCUs to store the firmware. For example, when you are booting your MCU, it first needs to read certain instructions, and all those codes are stored in the flash. Sometimes it is also used to store constant data. Now, flash retains its content even when the power is off. Now, depending on the microcontroller that you use, you see a lot of pins. Some may have 64, some might have even over 100 pins. Some of the pins are used for power, specifically the ground and the VCC pins. Now, the other pins are mostly used to communicate with peripherals. When I say peripherals in this instance, I'm talking about external devices like a temperature sensor, pressure sensor, motion sensor, whatever sensor that you have. An LED is one of the simple electrical devices that you can connect to a microcontroller, right? So you connect one side to ground. Normally we connect the shorter leg to ground, and you connect the longer leg to a different pin, a signal pin on the microcontroller. So what happens is you write a firmware on the microcontroller, and the microcontroller sends high or low voltage to the signal pin. If it sends high voltage to the pin, the LED turns on, and if it sends low voltage, that is 0 volts, then the LED is going to turn off, right? There is no power. The interesting thing about a microcontroller is not all these cool pins that are sticking out, or the design or the circuit board. The fascinating thing about a microcontroller is on the inside. Now, when we cut open a microcontroller, not like we are going to cut it open, but when we do, a microcontroller contains different types of peripherals. Inside the microcontroller, we have a CPU, we have ROM, flash, RAM, RCC is clock. We have GPIO and a lot of other peripherals like the UART and the SPI and I2C. A lot of them, okay? We cannot represent everything here. Now, all these peripherals that you see occupy a specific place inside the microcontroller. The same way your house is located at a specific place inside the microcontroller, every peripheral, including the core peripherals, the CPU, the ROM, the flash, the RAM, they are a specific address. Now, if you want to communicate with a particular peripheral, you go and you get the address of that peripheral. Now, let's assume that the first peripheral inside this microcontroller is the CPU, and because it is first, we are going to give it an address of 0. Okay, so now we have 8 zeros, and this number is in hex. If that is the case, and let's assume that each peripheral that you see here is 1 kilobyte in size. Now 1 kilobyte is 1024, 2 raised to the power 10. We can say that the first address starts at 000. 000, which means that the second peripheral, here is the ROM, will have an address of 0x0000400. Now 400 is in hex, and when you convert it to decimal, you get 1024. The third peripheral here, that is the flash, will contain an address of what? I think you can guess now. The address are going to increment by 1 kilobyte, 1024. So the first one starts at 0, the next one starts at what? 1024. Then the third one is going to start at 2048. Now 2048 in hex is 800, right? So the address of the flash will be 0x0000800, and the others follow suit. The address for the RAM will be C00, the address for the RCC will be 1000, and the address of the GPIO will be 1400. Of course, I'm not saying the 4 zeros, but they are part of the address. This is how easy it is to get the address of all the peripherals inside the microcontroller. So now, if we scroll up a little, you see all these pins, right? We call them GPIO pins, and the GPIO pins are part of the GPIO peripheral. If I want to connect an LED to this pin, it means that I need to go inside the microcontroller, get the address of the GPIO. When I get the address of the GPIO, then I can take it from there. There are different types of microcontroller unit architectures. We have 8-bit microcontrollers, we have 16-bit, 32-bit architecture. A microcontroller with a 32-bit architecture can address a memory space of 2 raised to the power 32, and that will give us 4 GB of space. So in a 32-bit microcontroller architecture, the size of the registers will be 32-bit. In normal sense, a register maybe is used for keeping stuff. You use a register to keep names of people or probably names of items. It is the same in microcontrollers. Now, a microcontroller has peripherals, right? We have RAM, we have RCC, we have GPIO. Now, when you pick one peripheral, inside that peripheral, we have registers. Different peripherals have different registers. So, for example, the RCC peripheral will have different number of registers compared to the GPIO. Just see registers as a space inside the peripheral, but actually it's a circuit that makes that peripheral act in a certain way. If you want one pin of the microcontroller to power an LED, you have to go to the register that is specific for doing that. For example, outputting data, and you write to that register or you read from that register. Let's scroll down here. Now, before we talk a little bit about registers, the inside of the microcontroller, when we lay microcontroller on a flat plane, if this is supposed to be the space inside the microcontroller, the first address starts here and the flash will be located somewhere there, and the RAM and the peripherals. When you pick one peripheral, the GPIO peripheral, it has a couple of registers. Let's say we have register 0, register 1, register 2, register 3. When you pick UART peripheral, it has a couple of registers. As I said, different peripherals have different number of registers for different purposes. I want us to take a look at some of the microcontrollers currently on the market and see what is going on inside. Okay, go to your browser. I use Google, but feel free to use whatever, and let's search for STM32G0B1RE datasheet right there. Click on the datasheet and yeah, there we go. Go ahead and download the datasheet. We also need something we call reference manual. By the way, in programming a microcontroller the bare metal way, the few things that you really need to embrace and learn to read are the datasheet and reference manual. They contain everything that you need to know about the address of peripherals, the address of registers, and how you can interact with specific registers. Let's search for STM32G0B1. This time we want the reference manual. Okay, so right here, download it. That is the reference manual. Okay, once you are done, I already have it. We will look at something. I'll start with the datasheet. Okay, this is our datasheet. I want you to search for block diagram. Block diagram. Yes. Now, this is the block diagram of the specific microcontroller that we are dealing with. It contains STM MCU. From the block diagram, you can see peripherals everywhere, okay? But I promise you, it is not confusing at all. At the center of this microcontroller unit is the clock source, that is the RCC. Now, when we go here, you can see GPIO, general purpose input and output. Inside the GPIO, we have specific ports, port A, port B, port C, up to port F. Now, each port has a certain number of pins. So now when we go back to this microcontroller, you can see it has pins, right? So probably this might be 16, 16, 16, 16, let's say 64 pins. It could be that all the pins here belongs to one port, port A. It could be all these pins belong to port B, port C. But don't forget the same peripheral, and the peripheral is GPIO. So GPIO, it has instances. It has port A, port B, port C, port D, port E, port F, and they are all GPIO. They are all pins that you can use for different purposes. I want you to come back to the center, that is the RCC. You can see some lines that are connecting peripherals to this central clock. Okay, look at this line here, like a pipe, and they've written AHB. Now, all the pipes that you see here, we call them bus. Okay, so this is a bus, and this bus is written APB. This is another bus, it's also APB. Let's see, this is another bus, is AHB. You can see there's one bus here that goes and connects to bus matrix. So this is also a bus. On the left side, this is DAC. DAC is also a peripheral digital analog converter. It means that if you have a digital signal, let's say a high or low, and you want to convert it to analog. So analog signal, it means that it fluctuates. So the analog signal that will be generated will fluctuate between 0 and 5 volts. ADC is another peripheral analog digital converter. So the DAC and the ADC, they work in the opposite way. Now the ADC, we use that to measure analog signals and convert them to digital. Let's say that you want to measure voltage. Okay, you have specific voltage and you want to use the microcontroller to read it. Then you have to connect that voltage source to the ADC of the microcontroller, and this peripheral will convert it from analog to digital. Now beneath it we have SPI, SPI2, SPI3. Okay, so the same peripheral, different instances. SPI is also another peripheral that is used for communication. Earlier on I said that some of the pins of the microcontroller unit are used to communicate with sensors. Different sensors also use different forms of communication protocols. So SPI is one of the communication protocol. UART is also one of the communication protocols. Now when you come here, you can see we have USB. I'm sure that you are familiar with USB, the USB that you use in charging your phone and other stuff. Yes, actually USB is a peripheral inside the microcontroller. If you have a PC in your home and there are USB ports, it means that the USB port is being connected to the microprocessor in your PC. So it is a peripheral inside there. The port that you see is just an extension to enable you to connect whatever you have to the peripheral. All right, now on the right you can see we have UART, which is also UART. All right, now besides these we have the timer peripheral. Let's say that you are doing something and you need to time stuff. We have the power control, we have some watchdogs. Okay, an event happens and you want to trigger something. Different peripherals inside the microcontrollers are used for different activities. Enough of the datasheet. Close it and let us take a look at the reference manual. Let's see what we got. You downloaded it, so go ahead and open it. Inside this reference manual, I want you to search for memory map. You scroll down a little bit. This is what we are looking for. This is the memory map of the MCU dev kit that I'm using. In a glimpse, you can see this memory map presents the address of all the peripherals and the components inside a microcontroller unit. Now, as I presented in the first page right here, every peripheral inside the microcontroller has specific address, right? So now this microcontroller, this is how it looks like. The flash memory occupies this address. You can see main, flash memory, system memory, and RAM. There is a part of the memory that is painted gray. It is reserved. You can't use that part. So we have flash memory, this part reserved. Here we have system memory. When you look at the left, RAM peripherals. Okay, all the UART, all the SPI, all the I2C, all the timers, they are part of the peripheral. On the right, the peripheral is extended into buses. Now, when we opened the datasheet, you could see that all the peripherals were connected to specific bus, right? I hope you've not forgotten. Take a look again. This is the block diagram. You can see all the peripherals are connected to a specific bus and the bus connects to the RCC. This point is where the AHB bus is connected to the APB bus. Right, for now, don't worry about the name of the acronym. Just know that AHB, APB, they are buses. So they are channels through which the peripherals are connected to a clock source. Every peripheral requires the clock source to run accordingly. All right, now pull the data sheet aside and let's look at the reference manual. The APB bus, it starts at this address 0x4000000. That was difficult to say. And it ends at this address 0x4000A7FF. Now, if you are wondering why we still write address in hex and not in decimal, copy this address and let's convert it. Go to your browser and type hex to decimal. paste this, make sure there is no space, right? Convert. Is it easier to say 1,073,784,831, or it's easier to just say 0x4000A7FF? Enough of that. Now go back to your memory map. There's a second APB bus that starts from this address and ends here. Now there's a gray area, which means it's reserved mostly. This bus, it starts from here and ends here. The IO port starts from here and ends here. Now these bus are important. The reason is that every peripheral is connected to a bus. The GPIO is connected to the IO port, which means that if we want to get to a particular GPIO peripheral, we can find that within the IO port address range. In the same way, the other peripherals like the SPI array is connected to the APB. Therefore, if we want to find the address of the SPI, we need to look at the range of the APB bus. To prove that, let us scroll down. If you look at this table, SRAM, which means that it's a special type of RAM. It has a starting address here. Now this is the flash memory, and the starting address of the flash memory is this, just as we saw in the memory map. All right, look, flash memory starts here. Let's find some of our known peripherals like the GPIO. On the bus side, we look for IO port, right? The boundary address 0x5000000 to this is occupied by this peripheral GPIO-A. The next range of memory, which has a size of 1 kilobyte, is occupied by GPIO-B and GPIO-C, D up to F. Flash is connected to the AHB bus, and the address range of the flash is 0x4002 2000 up to this, and is 1 kilobyte in size. Enough of the STM32 MCU. Let us take a look at other MCU. One of the popular MCUs is the Atmega, right? Because of the Arduino platform. Let us search for Atmega 2560 datasheet. Download the datasheet. Open it here. On the first page, it gives you some characteristics of the MCU that you are going to deal with. There's JTAG. We are interested in something that has to do with memory, so let's search memory map. This is address map with external memory. What about block diagram? This is the inside of the Atmega 2560 microcontroller unit, mostly called the Arduino Atmega. All right, so at the center is CPU. Now right here we have flash, we have RAM here, different types of RAM. Let's see what we got. We have a bunch of peripherals. We have the SPI, TWI is here. We have the AEP ROM. Now on this side, you can see port A, port G, port C, and definitely these are the GPIO ports. On this side, we have the UART 3, UART 1, UART 0. Commercially available microcontroller units. They come with multiple instances of the same peripheral. Okay, so the UART peripheral has few instances, like we have UART 3, UART 1, UART 0. The GPIO likewise, and the others too. Let us check on the registers and see. So here the AVR CPU general purpose working registers. The registers are laid out here. So register 0 up to 31. Each register has a definite purpose. Open the reference manual again. I want you to set the GPIO register. Every instance of a GPIO, so whether it's GPIO port A, GPIO port B, each instance has mode register. It has the output speed, the pull up, pull down register, the input data register, output data register. Now, one of the things that make embedded system very interesting, especially doing bare metal programming, is some of the registers. Their names are very self-explanatory. Okay, this is what I mean. Look at all the registers here. Literally, they are telling you what they do, which means that if you want to communicate with a particular GPIO peripheral and you want to read the input from that peripheral, then clearly you are going to deal with the input data register. In the same way, if you want to output something or write something to the register, then you can see right here, output data register. Now click on the mode register and the first register of the GPIO peripheral. You can see right here, it has written GPIO X mode R. The X just means that the peripheral has multiple instances. We have GPIO A, GPIO B, GPIO C. Okay, so if you are dealing with GPIO A, then this register will be GPIO A mode R. if you are dealing with GPIO C, then the mode register of that instance of the GPIO peripheral, that is C, is going to be GPIO C mode R. The microcontroller we are dealing with right now is a 32-bit architecture, which means that the registers are 32 bits long, starting from 0, 1, 2, 3 up to 31. It allows you to define how you want to use a particular GPIO pin. In case you want to use a particular GPIO pin as input, then you need to set the part that corresponds to that pin to 00. Now, how do you know? Take a careful look. We have mode 0, mode 1 up to mode 15. Now, each mode has 2 bits under it. What it means is that in regards to this microcontroller unit, that is the STM32 J0B1, inside this microcontroller unit, each GPIO peripheral has 16 pins. So from mode 0 to mode 15. Alright, now if I want to connect an LED to this particular pin 0, what I need to do is that I look at the mode that corresponds to pin 0. If I want that pin to put on or off an LED, it means that pin is going to act as output pin. I need to write this to bit 0 and bit 1. So I come here. This is general purpose output mode. The pin is going to act as output. Why? Because it will send volt to the LED. Bit 0 here to 1 and bit 1 here, I need to set it to 0. What if I want to connect the LED to, let's say, pin 7? Okay, easy. Pin 7 corresponds to mode 7. This is mode 7. What are the bits under mode 7? 14 and 15. Right here. It means that I need to set pin 7 as output mode. So what do? The first bit is bit 14. I set it to 1. The next bit I set it to 0. That is bit 15. In the same way, if I want to connect a button to the microcontroller unit, and when I press the button, I want the microcontroller to do something, I need to set that pin as input pin, so that when I press the button, let's say that the state will be high, and when I leave it, it will be low. If I want to connect the button to pin 8, then pin 8 corresponds to mode 8, right? Then I need to set this mode as what? As input. So I'll set bit 16 to 0 and bit 17 to 0. When we scroll down, we can see the other registers that we have. The data register, you can see, is read only. If I want to read a value from, let's say, pin 11, it means that I come to pin 11 right here and read whatever value is there. This is the output data register. And the output data register, you can write or read. These bits corresponds to the number of pins. Now from 16 to 31, they are reserved. This is a general overview. In the next video, we are going to implement writing and reading from specific registers. Let's assume that this is GPIO A and we want to write to pin 2. Go back to the reference manual and search for the memory map again. We know that the GPIOs are connected to the IO port. So scroll down. On this side we have the bus. So we will look for the IO port. And this IO port, starting from the base address, that is GPIO A, and they are laid down consecutively for GPIO A to B to C to D, and they are 1 kilobytes apart. We are going to start with GPIO A, but before that, just create a directory wherever you want it and create a file. I called it main.c, so you can include this. We want to set GPIO A, let's say pin 3, as output. This is what we want to do, and also after that we want to set GPIO B pin 5 as analog. Alright, we are going to do this. Go back to the reference manual and we will copy the base address of GPIO A. Now before you paste it, whenever we are addressing memory, we use the volatile keyword, and as we said, we are working on 32-bit architecture. We cast the address to 32, and inside here we just paste it, and we need to add something to it. Before that, make sure you close the gap here. As we explained earlier from our diagram, a peripheral contains a couple of registers. Go back to the reference manual and search for GPIO registers. These are GPIO registers. We have a couple of them. Click on the first one. Now we want to set pin 3 GPIO A as output. According to this, to set a pin as output, you need to set the first bit to 1 and the next bit to 0. Okay, we are dealing with pin 5. Pin 5 means that is 16 pins. Set mode 5 as output, so you set bit 10 to 1 and bit 11 to 0. Before we set that, just look on top here. Registers are arranged inside peripherals one after the other. If this is our first register, it means that it has an offset of 0. It's the first register inside the peripheral. Okay, so it has the same address as the peripheral. Now the next register is the GPIO OTYPER. Because this is 32 bits, that is 4 bytes. Okay, so the second register will start at this offset and it just goes on. The third will be 0x08 and the next one will be 0x0c, just increasing by 4 bytes. I want you to remember that. Go back to the VS Code and here we add the offset. Because we are dealing with mode R register and it is the first register, the offset is just 0. All right, so we do this as the offset. And now to set specific bit inside the register, first you have to make sure that it is cleared, right? So to do that, we have to end it with the number of bits we want to deal with. Each mode deals with 2 bits. So if we want to set 2 bits in here, then we have to look for a number that has, let's say, 2 ones in there that we can manipulate, and that number is 3, right? If each mode had 3 bits here, then when we come here, we actually look for a number that has, let's say, 3 consecutive ones, and that will be 7. All right, but now we only need a number that has 2 consecutive ones, and we can use 3 to do that. So we take our 3 and we are interested in pin 3. Okay, now pin 3 starts at bit 6 and bit 7. So come here and we are dealing with pin 3. 3 times 2 is 6. Okay, so we are going to shift 6 to the left. All right, so when we do this, and that is it, we have cleared a bit, clear bit 6 and 7. Now after clearing it, then we will set it to the particular mode that we want. I'll copy and paste it here. Instead of end, we will have to do all here, and we remove this. And because we only need to set bit 6 to 1, we can't use 3, right? Because if we use 3 here, it will set both bit 6 and 7 to 1, but we don't want that. We can use 1 like that, and this is going to set it. So by doing this, we have set pin 3 of GPIO A as output. Right now, the next one, we want to set pin 5 of GPIO B as analog. So the first thing we want to do is to go to the reference manual, get the address of GPIO B. Let's do that. So we come here, we search for the memory map, we will go to the IO port, this IO port, GPIO B, and the starting address is here. So just copy this, go to your VS Code, and we will do the same. We are pointing to address, right? So we have to cast it to volatile, and we are dealing with 32-bit. So we cast whatever address to uint32, paste the address that we copied, and now once we have this, we will go to GPIO B and get the registers. But don't forget that GPIO A, B, C, they are just instances of the same peripheral. Okay, go back again to the GPIO registers, you get the mode R register right here. Yeah, so it's 1 1. Okay, pin 5 corresponds to mode 5, and with mode 5 times 2 will give us 10. So we start from bit 10 and bit 11. We will set bit 10 to 1 and bit 11 to 1. Now mode R register is at an offset of 0x00. It's the same for different instances of the same peripheral. Okay, so the offset will be 0x00 here. Make sure you remove the space. First, you need to clear bit 10 and bit 11. Okay, we need 2 bits to do that, and 3 will help us. So we use 3, we move it to bit 10, clear bit 10 and 11. After clearing it, now we will set both bit 10 and 11 to 1. So I'll copy and paste this, and we will use all this time, because we need both bit 10 and 11 as 1, we are going to maintain 3. All right. If we wanted to set GPIO B pin 5 to output, we use 1 here. All right. We just use 1 over here. Yeah, that is it. Very simple. You get the address of the peripheral, you get the offset of the register you are dealing with, then you go ahead and you set your bit. All right. Now go back to the GPIO registers. What if we want to write something to a GPIO? Okay, let's say we want to write high or low to a particular pin of the GPIO. What are we going to do? Let's try that. Let's look for the data output register. This is the data output register. It means that whatever we write here will be written to the pin. If we write 0 here, then it means low, right? If you write any number here, it will be interpreted as high. So we just write 1 and it will be interpreted as high. So what if we want to write high to pin 9 of GPIO-C? Okay, let's write it here. Let's see. I think you guys can take a few minutes and work it out, but we will do it just as we did for the others. Okay, we'll go to our reference manual, go and get the address of GPIO-C. But if you watch closely, we said that the GPIO peripherals, that is ABC, they are at an offset of what? 400. So A is 000 and B is 0400. Okay? So you can see that C is going to be 0800. That is very easy, but not to confuse you, go back here and let us search for the memory map. Okay, once we have the memory map, we go to the IO port bus, and this is GPIO-C, right? So go ahead and copy this. You write the same thing, nothing different, volatile. You cast it to UIN32 inside here plus offset, right? So we write it here plus the offset of the register we want to deal with. This time we are going to write to the output data register. Okay, so we'll go back and get the offset of the output data register. Search for GPIO registers. Okay, so the registers are here. The output data register is this. We can see that the offset of the output data register is 0x400. All right, so you can copy that. When you come here, you add that. So write 0s14, and we just want to write high to this register, but not only this register, to a specific pin, that is pin 9, right? So we need to go back here. This is pin 9, and pin 9 is exactly at bit 9. Okay, so bit 0, bit 1 up to pin 9. Okay, so we are going to write high to pin 9. So go here, and this time we can just use all, right? And because we are writing high to pin 9, we can just shift this, right? And once we do this, basically we shift it to the left 9. So if we compile this program and we flash it to our STM32 board, whatever is connected to pin 9 is going to receive voltage. So if we have LED, then LED is going to set high. But I'm just curious, why don't you try write low to GPIO-C pin 9? What do you think is going to be? We want to write low to GPIO pin 9. Don't forget, GPIO-C pin 9 is already high. So if you want to write low to it, what do you think? Are you going to do this? If you do this, obviously 1 is shifted to the left 9 and we invert it, so we get 0. But since pin 9 is already 1, if you do 1 or 0, it will still be 1. Okay, so to do that, you have to use AND. So when we end 1 with 0, then we are going to get 0. Let's move on. We create a struct to represent the peripheral, and inside the struct we represent the registers with a 32-bit type integer. First, go to your reference manual, search for GPIO registers. These are all the registers of the GPIO peripheral. We are going to represent all these registers inside the struct. Create the struct here. We call it GPIO. We are going to reference memory, so always you shouldn't forget to bring your volatile keyword. We use the 32-bit int. Then you need to be careful here. Now all these registers, they are 4 bytes apart, that is 32-bit. So starting from mode R, then you go to the OTYPER, then you go to this, you go to that. You need to write them accordingly. If you, let's say you start with the mode R, and instead of writing this, you write this, then later if you want to address this register, it will be at the wrong offset. You are not going to get the correct results that you want. So place your reference manual close by and write them. So let's do that. The first register that we have, the first register is the mode R. The next one is the OTYPER, OSPDR. We go to the IDR, ODR, PSRR. Just come to the next line. LCKR, AFRL, AFRH. Then we have the BRR. Okay, so look here, the registers are 11. Okay, this is not a register, it's just GPIO register map. What is there? Okay, so when you go there, it actually gives you all the registers starting from the first, the mode, and their offset. Yeah, so we have 11 registers. That is it. Now after creating the struct, then we can just define our GPIO A. Then we will do as we did for here. So we need to get the address of GPIO A, then we will cast it to this struct. Write your define properly. We have our struct. We will cast it to point to this GPIO register, and we will get the address. Now this is the address for GPIO A. We just copy it here. Once you have this, I think you can just create the struct for the others. Now don't forget, this is a struct, so we have to bring the semicolon so that the red thing here goes. What do you think if we want to represent GPIO B peripheral? Obviously this is B, and this is easy. You look at the B and the A, and the difference is this, right? That is the offset. So what you can do is you can just add 0s400, right? But I prefer to put this into bracket like this. Once you get the concept, the rest is just easy, and that is 8. To make it consistent, then let's make GPIO A as 0. Now this is how you create a structure for a peripheral of whatever you want to deal with. When we looked at the GPIO peripheral, we saw the input moves, right? We can create an enumerator and we represent all these. Input is 00, which is 0. Output is 01, which is 1. Alternate function is 10. This is 2. Analog mode is 11, and 11 represent 3. So we do enum here, and the first 00 is input, right? We can do GPIO input mode, GPIO output mode, GPIO alternate function mode, and the last one will be GPIO analog mode. We have represented the modes for GPIO. The next thing that we can do is we can write a function that will clear the bit for us, and also it will set the bit that we are interested in. We can create a static inline function and call it GPIO set mode. If we want to, let's say we want to set pin 2 of GPIO A, we want to set it to analog, we call that function and we pass it into that. So come here and let's create the function. Let's make this static inline. It will not return anything. Let's call it GPIO set mode. So here we will give it a pointer to our GPIO structure. We will give it pin number, so we can just say pin, and also we will pass the mode that we want to set. Okay, this should be, let me close this. This should be a very easy function. We are just going to replicate this. Okay, first we need to clear the particular part of the register that we are interested in. But to be able to know where to clear, we need to find the shifting value. Now the shifting value depends on the pin number. So if we want to clear pin 5, when we look at the mode R register, each mode has 2 bits. So pin 5, we are going to start at bit 10 because we multiply by 2. Okay, so when we come here, we will use that mindset to do that. So instead of putting an arbitrary number here, we are going to put the pin and we multiply by 2. So whatever pin that we pass, we multiply by 2, and the 3 will remain. That should be fine. We will. Now we have passed a pointer to the peripheral, that is the GPIO pointer, and we need the mode R register, right? So we get the mode R register, we end it. We have 3. Now we just add U to make it unsigned value, right? Now we are going to shift this 3 depending on the pin that we have. And since, as I explained, each mode corresponds to 2 bits, we will get the pin and we will multiply it by 2. You can leave a comment. Once you have cleared a bit, then you can set it. Okay, to set it, we call the mode R, and setting we use the or instead of the end. Now there's something that we need to do here. When you look at how we were setting each bit, the setting of the bit depends on the mode that we want to. If we are setting the mode analog, then we are going to set a part of the 2 bits to 1 1. But if we are setting as input is 0 0. So this part depends on the mode, okay? And the mode has only 2 bits. These are all the modes. So when we end whatever mode we have with 3, we will get the mode that we want. Then we will shift this according to the pin that was given. So when we come here, we can do mode and 3. So let's assume that we are going to set that pin to input mode, and input mode is just 0 0. So it means here we pass 0 to it. So when we do 0 and 3, we are going to get 0. So once we have the 0, then we can shift it to the particular bit range that we want, and it's just the same as what we've done above. This should be easy. Now what it means is that whenever we want to set the mode of a GPIO, we just call this function. For example, we can do GPIO set mode. The first one is a pointer to the GPIO struct. So if we are interested in GPIO A, we call GPIO A over here. The next one is the pin. Let's say we are dealing with pin 3, and the next one is the mode. Here are all the modes, so we can pass GPIO input mode, and it's just like magic. So now we don't have to do all of this. We have just put everything inside a function right here, and we can call it. And actually this is the beginning of hardware abstraction layer. We are abstracting some of the hardware. Okay, so you are not going to write the registers yourself. We put everything inside the function, then we will call the function right here. There is a little problem. When you look here, we have to define each instance of GPIO. So if I need GPIO F, I have to physically write it here. So I'll define it, then I need to calculate the offset, right? When you look at when you go back to the reference manual, IO port, yeah, right here. So we have GPIO A, B, C, D. So if I want GPIO F, then I'll have to copy this address, right? But maybe there is an easy way that we can just write a generic function by looking at the offset here. The starting address, this is starting from 0, then the size is 1 kilobyte. So the offset is 1 kilobyte, 1 kilobyte, right? So we can just write the base address and we multiply each by a number. Okay, so if we give this the base address, then here this part we call bank because there's an increment and the increment is 1 kilobyte. If we pick the base address for GPIO A, the bank for GPIO A will just be 1 kilobyte times 0 to give us this 0. Okay, and the bank for GPIO B will be 1 kilobyte. Now 1 kilobyte in hex will be what? 0x400. So we have 0x400 times 1 for GPIO B. For GPIO C, it will be 0x400 times 2, 0x400 times 3. You see where this is going? Yeah, so with that we can just write a generic GPIO macro. So whenever we call that macro, we pass in the bank. So if the bank is 0, then it means that it is going to return GPIO A peripheral. If the bank that we pass into the GPIO macro is 1, then it's going to return the base address plus 0x400 times 1. So whatever bank we pass into this generic macro, it will return the corresponding GPIO instance that we want, right? So let's do that. Right under here, leave some space and let's define. It will be GPIO, and this one is going to take, let's say, this variable called bank. We want this to return the GPIO instance depending on the bank that we pass to it. So we call the struct here and we'll cast it to GPIO pointer. We get the base address. We are going to add that to the offset times whatever value the bank is, right? We can do this right here. As we said, if we pass 0 here, then it means here we are going to get 0x400 times 0. So this entire thing will be 0, which means that this GPIO is going to return GPIO A. If you pass 1, then this part will be 0x400 times 1, the same 1 kilobyte. So when we come here, we will get 0x500000400. If we pass 2, get 800. This macro will return whatever instance of GPIO that we want. Now, I think instead of calling GPIO set mode here and we pass the specific GPIO instance, right? It would be nice if we can do something like this: GPIO set mode, and we just pass a pin to it, then we pass the mode. So somehow let's find a way and combine the GPIO instance that we want. Let's say we want A or B, and we combine it with the pin number. Now when you look here, the pin is just 1 byte containing the pin number. So we can make this pin number 2 bytes so that the higher bytes will contain the bank. Now when I say bank, I mean A, B, C, D, alright? The higher byte can contain the bank number, that is the pin bank, and the lower byte will contain the pin number. Example, we have this pin GPIO A pin 7, right? This is GPIO B pin 9. So when we call this, we will do something like this: set mode, and here we got the pin and we want to set it to output. We can do something like this. Let us create a macro that the macro will take the bank and also the pin number and combine them, okay, and it will return pin. Go right beneath this one, let's define this macro and we call it pin. Okay, so this macro will take the bank, as I said, and it will also take the pin number, and we want it to combine them, put the bank inside the higher byte and put the number inside the lower byte, right? To do that, let's say we have the first bracket here for the higher byte, and we will do OR with the lower byte, that is the num. So whatever we get, we will OR it with the num. We want to put whatever value that we get into the higher byte, right? So whatever we get here, we have to shift it to the higher byte before we OR it with the number, so that the pin number will occupy the lower byte and whatever we get here will occupy the higher byte. So inside here, we want to get the bank and we will subtract A from it, so that, for example, if we are dealing with GPIO A, then the bank will be 0. If the bank is 0, for example, we call the GPIO, we pass 0 in, it will return GPIO A peripheral. We will create 2 macros that when you pass, let's say you have a pin, right? A pin that consists of the bank and the pin number. When you pass that pin to it, the pin number macro can subtract the pin from it, and also a pin bank macro that will subtract the bank from whatever pin you pass to it. You should find a way to separate the pin number from the pin bank. Let's call this pin number, and pin number is going to take pin, and we know that pin is occupying the lower byte, right? So when we end it with 255, you can do this, okay, or you can also end it with this and it should give you the same thing. Then we will make the macro for the pin bank. The same thing, you pass pin to it and this pin bank is going to get the higher byte, right? So you shift it 8 bits. Once we have these macros, we can create a more sophisticated form of the GPIO set mode. In the new function, instead of passing a pointer to the GPIO struct and giving it a pin number and the mode, we can just give it a pin and mode. So when we go inside, we can use our macros to get the pin number and the pin bank from the pin that we will pass to it, and we can do the same thing, right? Let's write it and see how it will work. I'll just copy and paste this. All right, let's call this mode X, more like a superior mode X. We don't have this anymore, and now we are using 2x for this all that we have. So here we will call the struct GPIO, a pointer to GPIO struct, and we are calling the GPIO macro to return the GPIO instance that we want. Now this requires a bank, right? Now we have a macro that will give us the bank, so let's call the pin bank here. The pin bank requires a pin that is 2 bytes, and it will shift it right 8 bits, and it will return the bank that we want. All right, we will pass the pin to it just like that. Once we do that, we are good. Now the new pin that we form, we put the pin number inside the lower byte. All right, so we will get the pin number. Let's just name this N to avoid confusion. So this one we'll call the pin number here, and the pin number requires a pin that is 2 bytes, and it will get the first byte. So we pass the pin to it, and easy, uint 8. Now if you are wondering how we are going to use this and how we will create this, to create this pin is very easy. So when we come here, we can do uint 16, right? Let's say we want to create pin A7. All right, how are we going to do it? Our macro is here. We pass the bank and we pass the number. We said we are interested in pin A7, that is GPIO A pin 7. So we pass our bank here and we pass the pin number here. Now you see how easy it is, and this is why using hardware abstraction layers is very important in embedded system, because you don't want to be calling the registers at every point. All right, what if you want to create, let's say, GPIO B pin 13? Okay, so we will do this as usual, 2 bytes, pin B pin 13. So all that we have to do is we pass B to it and number 13. Okay, so once we have our pin like this and we want to set the mode for this pin, we need to call this function. This is how we are going to do it. We call GPIO set mode X here, right? We pass pin A7 to it and whatever mode that we want, GPIO analog mode. Now you see the mistake that we made here. We are calling this pin A7 and we are passing AN7, but we forgot to call the macro that is supposed to create it. This is the macro, right? Put the macro right here and put the macro right here. Yes, we need a comma here. Now this is giving us red because we are calling it outside main function. You know, to run C program you need to call it inside main, and we are calling it here, so I don't really worry about it. Now this is a very good foundation for what we are going to do next. We are going to look at how the boot system works. We will write everything, how we are going to compile this. Hello everybody, let us look at interrupts and how the MCU boot. Interrupts are signals that temporarily pause the normal execution of a program, diverting the CPU to execute a specific function called interrupt service routine or interrupt handler. They allow the microcontroller to respond to events that require immediate attention, such as hardware triggers. If you look at the diagram that we have here, there is a button. When the button is pressed, the person pressing the button is expecting the CPU to execute something, right? So during hardware triggers or even software generated events, interrupts play a crucial role in ensuring responsive system behavior, especially in embedded systems. In this diagram, we have CPU here representing our microcontroller unit. Inside the microcontroller unit, it has a program counter. The program counter is responsible for moving to specific instruction to be executed. Now when this button is pressed, the corresponding interrupt service handler from the vector table is loaded and executed. So a vector table is nothing but a structure that contains interrupt handlers. So you can see them as addresses to specific interrupt routines that we need to be executed. The MCU boot process and the vector table are very simple. When an ARM microcontroller powers on, and typically most microcontrollers, it reads a structure called the vector table located at the beginning of the flash memory. When we look at the CPU, we said that the CPU contains flash and RAM and other stuff. This table holds 32-bit addresses that corresponds to interrupt handlers. 1, 2, 3, 4. They are 32-bit addresses. Why? Because we are dealing with a 32-bit architecture. Now, the vector table begins with 16 standard entries defined by ARM, and this is common across all ARM-based microcontroller units. These entries handle core exceptions functions like reset, fault handling, and system interrupts. The remaining entries are specific to the microcontroller and correspond to peripheral interrupts, such as timers, communication interfaces, and GPIO interrupts, right? So let's say if you get Atmega or you get STM32, all these are built on ARM, but they support different peripherals. Some might have 5 GPIO instances, some have 3 UART instances, but across all ARM MCUs there are 16 standards. STM32F429, it has 91 peripheral interrupt handlers in addition to the 16 ARM standard entries. Each entry in the vector table points to a function that is executed when corresponding interrupt occurs. All these interrupts, they are addresses that are pointing to a function that needs to be executed. However, the first 2 entries are very essential to the boot process. So in respect to our diagram, it will be interrupt service routine 1 and interrupt service routine 2. The first interrupt service routine that is placed on top of the vector table is the initial stack pointer. This defines the address that initializes the stack pointer. And the second interrupt service routine is the reset handler. This one contains the address of the firmware entry point, the function executed when the MCU boots or resets. So we have to be careful here. To ensure correct operation, the firmware must correctly populate these entries, particularly the second entry. What is the second entry? We said the second entry is supposed to be a reset handler. It needs to be there as the microcontroller jumps to this address to begin execution during the boot process. We are going to write firmware that will load all these interrupt service routine into their proper place in the flash. I want you to go back to your VS Code. We will start with a reset function. Now inside here, infinite loop. The next function I will write will be point the stack. This will be defined from the linker script. We will create this file later. The next, we will define the 16 standard and the 91 specific interrupt service routine handlers. I'll call session. Inside the session, vectors contains 16 plus 91. So inside this, we call the e-stack and the reset function that we created above. Okay, so this is constant, make it S. This code snippet represents the minimal startup code for an STM32 microcontroller. It defines the initial entry point of the program and it set up the interrupt vector table. As you can see something here, vector. The reset function. Inside here, naked and no return. They are keywords from the GCC compiler. It specifies that this function does not return and does not use the usual function prologue epilogue. Inside this reset function is an infinite loop. It prevents the program from continuing execution as no actual initialization or logic is present yet. We've not done that. When we go to the next code fragment, it declares the external symbol e-stack, which is defined in the linker script. We are going to write a linker script soon and we will define that. Now, this typically points to the top of the stack memory. The next code fragment, which you can guess, it is creating a session in the memory and calling it what? Vectors. It places the table in a special memory session called vectors. What table? The vector table, as we already discussed. The tab is an array of function pointers that represents the interrupt vector table. The first 16 are standard, the rest depends on the MCU that you are using. Inside here, we are calling the e-stack and the reset. It means that the first entry e-stack, it defines the initial stack pointer address. The second entry, reset, it specifies the reset handler, the function executed when the microcontroller boots or reset. There will be other entries, okay, but the remaining entries can be filled with pointers to standard exception handlers and STM specific interrupt service routines. This forms the foundation for initializing the system that we are building right now. I hope you guys are ready, because in the next video we are going to write the linker script. We are going deep as we can, very low level. If you are afraid, maybe this is the point that you stop. If you are brave, why not? Come with me. Hello everybody. A linker script tells the linker how to map your program's sections like the test, the data, and the BSS to the memory layout of your microcontroller. Think of it as a blueprint that helps your code live in the correct places in the flash and RAM. Breaking down the linker script, there are four main parts. We have the entry, we have the memory block, the stack initialization, and the last part is the sections block. So this is what we are going to do. I want you to go to where your program was created and create a file and call it link.ld. Now in this file, we are going to write the linker script for our simple program. The first part is the entry, write entry, and inside entry, we will write our reset. And right beneath that, we will declare our memory block. Now, before we write the memory block, I want you to open your reference manual. I'm using the STM32 J0B1 RE board. From the reference manual, the starting address of the flash 0x08000000. That is a long number. Now, on the left right here, the RAM, which starts at 0x2000, then 4 zeros. In the linker script for the memory block, we are going to declare the starting address of our flash and RAM and also the size of each. When we scroll down, the starting address of the RAM was this, and it has a size of 144 kilobytes. On top of that, we have another section, but it's reserved. We will also look for the main memory flash that starts at an address of 0x08. It's right here. It has a size of 512 kilobytes. This is what we need to write the memory block of our linker script. Come back here. So you just write memory, just like that. You open your bracket and we can start with the flash. Inside here, put IREX. I will explain in a bit, but more importantly, we want to write the address. That is the starting point. Okay, go back here. This is the flash and this is the starting address. Let me just copy it. Let's paste it right here. Make sure you close the space. We will bring comma and we will write the size. Okay, instead of using size, we will use length. Okay, so let's just write length, and the length was 512 kilobytes. On the next line, we can declare the SRAM. Now inside the SRAM, I will put RWX. Let's do the same, right? Origin, and let us copy the origin for the SRAM, the starting address. Copy it and let's paste it, remove space, and also the length is 144 kilobytes. Now, if you are using a different microcontroller, just look at your reference manual and write these dimensions accordingly. The explanation is really simple. Okay, the first part is entry. All that we are saying is that we are specifying the entry point of the program, which is typically the reset handler. You remember when we were talking about the interrupt service routine, we said the second interrupt service handler in the vector table is reserved for the reset function. Exactly. Okay, so we are specifying the entry point, and we are also telling the linker where execution should start after the microcontroller powers on or reset. Now with the memory session right here, we are giving the starting address of the flash. Inside the flash, we have RX. So the RX indicates that the flash is readable and executable. So whatever we put inside the flash can be read and it can be executed. Things like test and read-only data are stored inside the flash. What we are doing with the second line is that we are indicating the starting address of our RAM and we are allocating amount of data storage for the stack. The RWX permissions allow for reading, writing, and execution. The next section is the stack initialization, and as we said, the RAM is for data storage and stack. So we are just going to point our stack to the last part of the RAM so that when values are added, the RAM will keep on coming down, and when values are removed, the RAM goes back up. So right here is stack, and the origin will be our SRAM. We want to point to the last part and we bring a comma. Very easy. The E stack, as you can see here, is set to the top of the SRAM, which is the end of the defined memory region. The stack will grow downward from this address during program execution. So whenever you call a function will be placed on the stack. You call another one, it will be placed on the stack, and the stack keeps on growing downward. And when you remove item, it goes back to the highest point of the RAM. The next block is the sections block, and this is where we map specific code and data session to their respective memory regions. So quickly, I want you to create that block. Let's call it session and open a big curly bracket like this. And on top of it, we will write vectors. You remember the vector table? Yes, we will write it here, and inside we will do this keep. Let's add 2 more parts here, and the last part will be the read-only data. Now, what we mean by this is right here. The vector table, which holds the interrupt and the exception handlers, is placed on top of the flash right here. The keep directive ensures that the vector session is not discarded by the linker, even if it seems unused. So we are making sure that it keeps the vector table right on top. The .test section, it holds the executable code, and the .arrow data right here, it contains read-only data. For example, the constants that we are going to use, they are read-only. You can change them. Both of these are stored in flash memory since they do not change during runtime. Leave some space and let us write the data section. The data begins, it ends, come after the curly bracket and SRAM flash. This section, that is the data section, it contains initialized variables. During startup, they are copied from the flash where they are stored initially to the SRAM. Now, the S data, start data, it marks the start of the data in SRAM, and the end data, it marks its end. The at flash you see here, it ensures that the initial values are stored in flash. SI data here, it holds the flash address of the initial data used during the startup process to perform the copy. So when you are starting, the data is in the flash and load the data from the flash into the RAM. What about the values that you don't initialize straight away? Well, they will go to the BSS session. So let's write that. .bss. At the end of the curly bracket, we are putting this in the RAM. The BSS section, it contains uninitialized variables. These are placed in SRAM and are cleared to 0 during startup. Whenever you write a code and you just declare a variable like int age and you do not initialize it, you leave it like that, it will be set to 0. Underscore SBSS and the EBSS, they mark the start and the end of the BSS section. The last part of our linker script will be alignment. We will do .equal and we write align into bracket, we write 8. After that, we can bring this and we will end our linker script. The align ensures memory alignment for performance and compliance with the microcontroller's architecture. Now, if you go to the first video in the series, maybe you can see it right here. We said that microcontrollers come in different architectures. So basically, the linker script will organize your program in a way that matches the memory layout of your microcontroller. It places the code and constant data in flash. It initializes the variables in the SRAM, and it will set up the stack at the top of the SRAM. By understanding this, you can customize your linker script to fit your specific application needs, such as adding custom sessions or optimizing memory usage. If you found this explanation helpful, don't forget to like, share, and subscribe for more videos in our bare metal programming series. See you in the next video where we will load the linker script into our projects and test it out. A Makefile is a script that automates the build process of your project. It defines rules for compiling source files, linking object files, and generating the final firmware binary, because we need the binary to flash onto our microcontroller. In your project directory, create a file and call it Makefile. Make the M capital. Makefile has few parts to it. First, we will define some flags for the compiler. The compiler flags variables contains options for the compiler. See flags. The first part right here is targeting the ARM Cortex M0 processor. If you are using, let's say, M7, then you need to define it as such. The M-term is just enabling term instruction set for better code density. The WAR enables compiler warnings, and the W extra enables additional warnings as well. So you might ask, what are the purpose of the flags? These flags catch potential issues early in the development process. The second part of the Makefile, we are going to define flags for the linker. LD flags. stlink.ld, it specifies the linker script for memory layout as we have defined in our linker script. Now the last part, no std library, it prevents linking with the standard C library. After we have defined our compiler flags and the flags for the linker, we will include some libraries in our firmware. Define libraries. We are only adding 3 libraries here. The first one, LC, it is linking the standard C library. The second one, it is linking the math library, and the LGCC is linking the GCC support library. The essence of writing a Makefile is to be able to generate a binary file that you will then flash onto your microcontroller. So these are the steps that we are going to go through to generate our binary file. We are going to build a target, that is the binary file that we want. Okay, firmware.binary. In order to get the binary file, we need a file that we call elf. Okay, elf file is when you have an object file and you link all the necessary libraries to it. And before we can create the object file, we need to compile the source code. The source code is this file, the main.c. So inside your main.c, make sure you've cleared everything with only this remaining. All right, go back to your Makefile. We do build and we call this firmware.bin. Now this depends on an elf file. Let's deal with the source file because we have it. We compile our source code into object file. The object file depends on the source code and small c here. This is the command from the ARM-GCC library, and this will enable us to compile the source code here into an object file. Now this sign represents our dependence and this $@ is representing our object file. The next stage here is that we'll add our links, right? The linker script and everything to this object right here. We are going to do that to create the elf file. At this point, we need the elf file, right? So we do elf, and the elf file depends on the object. The C flags already defined on top here, so that is no problem. The arm command, and this is where we add all the external libraries and our linker script. That is, we define the memory segment, everything we add to the object file. Now we can generate the binary file. We can do firmware.bin, and this depends on the elf. Okay, so with this command, we are compiling the elf file right into the binary file that we want. We go to the terminal and we run make. Is going to give us the binary file. But before we do that, we will just add a command to clean in case we want to reset. And also we add a simple command to flash the binary to the microcontroller that we are using. All the objects and the bin files that we created will be removed. The last line of code is to enable us to flash the binary that we create onto the microcontroller that we have. We are just calling the Stflash2, and we first need to call the reset, and we'll write it to this is the address of the flash. We want to know the details behind everything. We are not going to use IDEs, and because of that, you need to install the Stflash2. This is provided by ST company for flashing binaries onto the microcontroller. I have included the instruction for installing the Stflash2 in the description. So whether you are using Mac or Windows or Linux, go ahead and install it. Once you are done, go to the terminal where your projects are. And at this point, you can just call the make. Is going to compile everything. It will give us the object file right here, and more importantly, it will also provide the firmware.bin. okay, so with this firmware.bin, we can just call make stmflash. Once we run this command, it will flash our bin program to the microcontroller that we are using. You can go ahead and do that. One thing that you can also do, once you have the st2 installed, you can use the terminal to check the properties of the st that you have by using the stinfoprobe command. So I have the STM32 F74 connected to my machine right now. This is the RAM and this is the flash. Once you flash the program, it will just show the bytes that were read into the flash, and there you have it. In the next video, we are going to use all the knowledge that we have acquired and build our first Blinky project. Hello everybody. In this video, we will bring together everything that we have learned so far to build our very first Blinky project. Now we will start by first defining macros for extracting the pin bank and other necessary configurations. Okay, the first macro bit allows us to write to any bit that we want. The second macro is allowing us to combine a bank and the number to form one variable. Now in that variable, the highest 8-bit contains the bank number right here, and the lowest 8-bit will accommodate the number, which means that if we have an LED that is connected to, let's say, GPIO A pin 4, the bank will be A and the number will be 4, right? Now once this macro is called, it will give us only one variable. When we have that variable and we want to extract the pin number, because the pin number is occupying the lowest 8-bit, we can end it with 255 to get the pin number. And when we want the pin bank, we can shift it right 8-bit to get the pin bank. Once we are done with defining the macros, we will define a structure to represent our GPIO peripheral. Now this will interact with the microcontroller's GPIO registers more effectively. As we have done throughout this series, look at your reference manual, the structure of your GPIO peripherals and your RCC peripherals, and define accordingly. Now once we are done with defining the structure, we define a macro of GPIO, right? So if you want to work with GPIO A, here is going to be 0, GPIO B here is going to be 1, right? And since the GPIO registers, they are at offset from each other, as we have already talked about in this series, we just multiply the offset by the bank and it will increase accordingly. So depending on what you want the GPIO to be, we need to define the mode. So once we have already defined the states that our GPIO can take, then we will write a function that will allow us to set the pin to that particular state. It will be a static inline function. You will pass the pin and the mode. The GPIO set mode function will take as inputs the pin and the mode. The pin, as we defined in this particular macro, contains the bank and the num. We can use the GPIO macro and the GPIO bank to extract the particular GPIO peripheral that we are dealing with, right? So the first one will return the bank, and when we pass the bank to the GPIO macro, it will return the peripheral. Also, we can use the pin number to get the particular pin number that we are dealing with. Now once we are done, we can go ahead and first clear the area that we want to set, then we will set with this line. One thing that we have to note is that some microcontrollers automatically power and enable all the peripherals, that is from startup, but the STM32 is different. In order to preserve or save power, it doesn't power all the peripherals automatically, which means that to enable a peripheral, you need to allow clock to it. We have to create the clock peripheral, and according to my microcontroller, the clock, as we discussed earlier on, is the RCC peripheral. So let's define that. Now to define the clock peripheral, let us take a look at the reference manual. I will search for RCC. Now these are all the registers for the RCC, starting from the control register to configuration register up to this part, clock configuration register, right? So we are going to define all these registers and look at your particular MCU and define the same. I'll close this and we'll write strat RCC. Don't forget to always use the volatile because you're accessing memory. The first one is the CR. Okay, that is for the struct, and we will define the macro RCC. Now we are going to cast the address to this peripheral. Let's check the memory map. Okay, so this is our RCC and it has this address. So go ahead and copy and just put it in here. Okay, now we can use the RCC to enable the GPIO or any other peripheral that we are interested in. Since we are going to blink an LED, we need a function that is going to write to a particular GPIO pin, right? So this function will allow us to toggle the LED on and off. This is going to be static inline function, GPIO write. You pass the pin and also a bool. So first we will get the GPIO that we want to write to. Now once we have the GPIO peripheral that we are dealing with, we can call the bit set reset. Depending on the boolean that we pass, we either write to the first half of the register or we shift it left 16 so that we go and write to the second half, which means that we are going to reset the particular pin that we are dealing with. std bool right here, yes, and we are good to go. Inside the main function, that is where we are going to call all these functions that we have defined above, whether we want to set a particular pin as output or input, and also we go inside the loop and we will switch on or off the particular pin that we are dealing with. So come here and let's write the main function. Now we come here and we define our main loop. This is where we will write to the GPIO that we want. So we write LED true. In this code, we are putting the LED on and we are putting it off. But we can see there is no delay in between here. So the switch will be too fast that we will not be able to see. Let us define our own delay up here. So come here and write static inline delay. We just pass a counter to it. So we are not doing anything particular with this function. Whatever value we put up here, it will loop until the value gets to 0, okay, providing us a delay. So in between this, we can call delay and we can put in, let's say, 100,000. Now before running this code, we need to modify the startup code. Since we have added new data to our program, as you can see, we must ensure it gets copied to the correct place in the RAM region for execution. So come down here and inside the startup code, let us go ahead and define the BSS and the data section. So if you have not watched that one, take a quick look. It's part of the series. Start BSS session here. Okay, so with this code we can see we are defining the start BSS session and BSS session, the start and the ending sections of the data, and we are making sure that we are moving the BSS to the RAM. Once you have this, that will be all for our Blinky project. You can go ahead and run Makefile in your terminal. Thank you so much for watching this long series with me, and I really hope that you guys learned a lot. Bye. See you in the next video.